The key to opening the door to the mysterious universe. Non-Euclidean geometry. Opening statement by Alan Liu. What is science? We have concluded two simple and important conditions. Number one, scientific experiments should be able to be repeated. Number two, the theory of science should have formulas. Formulas should have a source. They cannot come out of nowhere or arise from thin air. It is pseudoscience without these two conditions. What is space? Space is made up of points, lines, and planes. Point. Point is the most basic element of space. Line. Line is the shortest distance between 2 points and its extension. Equal length of segments satisfy overlapping axioms. Plane. Take a point on a line as the origin and rotate 180 degrees to form a plane. Any area will satisfy overlapping axioms. Space. Take a straight line on the surface as the axis and rotate 180 degrees to form a space. Any volume will satisfy overlapping axioms. In space, is it possible to find a time axis? Rotate 180 degrees to form a space-time? Obviously, you cannot. Time has been increasing, and it cannot be reversed. So it is impossible to find a fixed coordinate in space-time. That means there is no such thing as a space-time. Meanwhile, space-time can never be repeated as an experiment, and therefore, it is pseudoscience. Most people believe that lines in non-Euclidean geometry are curves. This is wrong. In any geometry, a line is a line and a curve is a curve. Most people consider non-Euclidean geometry difficult. In non-Euclidean geometry, it is believed that a straight line is a curve. However, this idea is not easily understandable. Very few people know the true face of it. In fact, it is the same and as simple as Euclidean geometry, as long as you do not confuse yourself. In non-Euclidean geometry, a straight line is not a curve. A straight line is always a straight line. Generally, a straight line in non-Euclidean geometry is drawn as a curve. It is for the purpose of comprehension only. For example, if we draw the 3 straight sides of a triangle, the sum of the 3 inner angles will appear to add up to 180 degrees. This triangle does not look like a triangle in non-Euclidean geometry. In order to make the inner angles and the appearance of the triangle greater or less than 180 degrees, we have to draw the 3 straight lines as curves. Although drawn as 3 curved sides, we must think of them in our minds as straight lines. Because if you are really in the space of non-Euclidean geometry, the 3 triangular sides you see are straight, but the sum of the 3 inner angles do not add up to 180 degrees. In any space, whether Euclidean or non-Euclidean, when we see a straight line, it is a straight line, and when we see a curve, it is a curve. If you are in Euclidean space, when you see a curve, you cannot assume this curve is a straight line in non-Euclidean space. And so, you also cannot assume this Euclidean space is a non-Euclidean space. These assumptions are wrong. It was so bad that Einstein himself saw the curve in Euclidean space and treated this curve as a straight line in non-Euclidean space. I apologize. In this book, there are some lines that are drawn extremely curved. If you still treat a straight line in non-Euclidean space as a curve, you will have difficulty learning non-Euclidean geometry. In any space, whether it is Euclidean geometry or non-Euclidean geometry, The minimal space is an Euclidean space. In the almighty universe, Earth is like a drop of water in the ocean. Therefore, the geometry for the region of Earth is an Euclidean space. The light, that is 1.74 seconds bent by Einstein's so-called gravitation. This light is the curve of Euclidean space. But Einstein took this Euclidean space to be non-Euclidean space. And then he treated this curved light as a straight line of non-Euclidean space. This is absolute nonsense and not to be believed. Einstein added that from the above gravitational action, he believed that the universe is the elliptical space of non-Euclidean geometry. This is even more ignorant. Earth itself is so small, so how can one say the Earth comprises the entire universe? How can one see a patch of grass and say it is a forest? And so, Einstein chose the wrong conclusion for elliptical space. The universe can be any kind of space, but not elliptical space. If the universe is an elliptical space, when we see a star in the east, we can also see the same star in the west. Moreover, the light and heat emitted by millions of stars can only circulate within the universe, and there is no way for them to escape. After billions of years pass, the whole universe will be so bright during the day or night, and the temperature of the entire universe will rise to thousands of degrees. Are all Riemannian geometry non-Euclidean geometry? No. Riemannian geometry has two different geometries of the same name. It is easy to misunderstand. There is no relationship between the two. If you are not a mathematician, you are not able to tell the difference. If you are a mathematician, you are still not necessarily able to tell the difference. One Riemannian geometry is part of differential geometry. This kind of Riemannian geometry studies the problem of manifold in Euclidean space. Chen Shangshen, a famous Chinese mathematician, is successful in this Riemannian geometry. The other Riemannian geometry belongs to non-Euclidean geometry. Euclidean space cannot contain a non-Euclidean space. In fact, no space can contain any other space. In order to avoid misunderstanding, it is best to call the non-Euclidean geometry of Lobachevsky geometry only as hyperbolic geometry, and the non-Euclidean geometry of Riemannian geometry only as elliptic geometry. To be called hyperbolic geometry and elliptic geometry is not quite perfect, because non-Euclidean geometry has nothing to do with the hyperbola or ellipse. There may be a certain degree of comprehension for beginners, but the plane in hyperbolic geometry is not a hyperbola, and the plane in elliptic geometry is not an ellipse. So, on the contrary, this makes it harmful to learn. If there is a more appropriate name, that would be best. Clearly, a curve has curvature. But how come a straight line also has curvature? A straight line of non-Euclidean geometry is not a curve. So why does a straight line of non-Euclidean geometry have curvature? Yes, a straight line of non-Euclidean geometry has curvature. Thus far, people consider this a bizarre phenomenon and an utter mystery. I have read a lot of non-Euclidean geometry topics, but have not come across this correct concept. This space curvature is derived from the characteristics of space and is similar to, but different from, general curvature. Every space has its own spatial characteristics, and its own curvature. This curvature is sometimes called the space constant or the cosmological constant. Let me offer a simple example. Water and glass all have different refractive indexes, and we use light as a straight line. Before we do anything, let's first define parallel lines. Parallel lines are the lines between intersecting and non-intersecting lines. In water, if there is only one parallel line, we understand that this is Euclidean space. Because of refractive indexes, there is no way to guarantee that two parallel lines in water will intersect or not. There is no way to reach the point of infinity to confirm it. Even so, there are only three possibilities in theory. Number 1. The parallel angle is less than 90 degrees, and there are two parallel lines. This is the hyperbolic geometry of non-Euclidean geometry. Number 2. The parallel angle is equal to 90 degrees, and there is one parallel line. This is Euclidean geometry. Number 3. The parallel angle is greater than 90 degrees, and there is no parallel line. This is the elliptic geometry of non-Euclidean geometry. If the second condition is true, there is no issue, and this is Euclidean geometry. If the first or third condition is true, it is clear that these two lines may have curvature. Euclidean geometry already has a complete set of theories and formulas. In fact, this is the same for non-Euclidean geometry. In current day, we only discuss the history of non-Euclidean geometry, or aspects, like the sum of the inner angles of a triangle in hyperbolic geometry is less than 180 degrees, and that elliptic geometry is spherical geometry. However, it's just that people don't know that the first and third conditions of non-Euclidean geometry already have a complete set of theories and formulas. In other words, if there are formulas for Euclidean geometry, then there are formulas for both non-Euclidean geometries. Curvature of non-Euclidean space. The curvature of a line in Euclidean geometry is the curvature of non-Euclidean space. How can we prove the curvature of non-Euclidean space? There is consistency between non-Euclidean and Euclidean geometry. Aside from the various theorems associated with parallel lines, Euclidean and non-Euclidean geometries are the same. In early times, people thought that only Euclidean geometry and Euclidean space existed. People did not expect that there existed a non-Euclidean geometry, and that non-Euclidean space has a curvature. No one had defined it yet. Now it is time to define curvature for non-Euclidean geometry or non-Euclidean space. We define curvature of the infinity sphere as non-Euclidean curvature. Infinity circle, the center of a circle at an infinite point, or r equals infinity. Infinity sphere, the center of the sphere at an infinite point, or r equals infinity. Before we prove the curvature of an infinity sphere, we need to prove the curvature of an infinity circle. Curvature of an infinity circle. See picture on the right. Let the arc of ACB equals S be the arc of the infinity circle, T be the tangent length of A and B, alpha be the tangent angle of A and B. From section 127 equation 2, we have cosine pi minus alpha over 2 equals hyperbolic tangent T over K, where K is the constant of curvature. Therefore, sine alpha over 2 equals hyperbolic tangent t over k. If the arc of ACB approaches 0, then 2t approaches s. Therefore, sine alpha over 2 equals hyperbolic tangent s over 2k, and therefore delta alpha equals delta s over k, and therefore delta alpha over delta s equals 1 over k. Thus, the curvature of an infinity circle equals delta alpha over delta s equals 1 over k. From the definition of the curvature of a sphere, we have curvature of space equals curvature of sphere equals delta alpha over delta s squared equals 1 over k squared. As space consists of straight lines in non-Euclidean space, then that means non-Euclidean space is straight. As there exists curvature in non-Euclidean space, then the straight lines of non-Euclidean space also have curvature. Example: if non-Euclidean space is filled with water, then the light inside the water is a straight line. And so, this space of water is straight and not curved. However, there is a refractive index in the space of water, and so this space has curvature. Hence, its straight line also has curvature. The non-Euclidean space is straight, but with curvature, and so do its lines. Therefore, the non-Euclidean universe is straight with a curvature, and so do its lines too. Can you accept such an explanation? Consistency of space. Since the discovery of non-Euclidean geometry, mathematicians have been trying to prove the consistency between Euclidean and non-Euclidean space. But their methods for proof are too abstract and difficult to understand, and I believe those methods do not actually answer the question. For the average person, he or she may consider long, complicated calculations and even incomprehensible proofs as the most remarkable ones. Einstein's general theory of relativity is the best example. In fact, many people use his theory to fool others. The best proof is one that is simple, clear, and people understand and believe it. As we know from the book of Non-Euclidean geometry, k is the space constant of non-Euclidean space, while 1 over k squared is the curvature of non-Euclidean space, and space curvature is a real number. And if it can be proved that the curvature of Euclidean and non-Euclidean space are all included in this real number, and vice versa, and any real number represents a curvature of Euclidean and non-Euclidean space, then this is the consistency of Euclidean and non-Euclidean space. If the above conclusion is true, then there is consistency between Euclidean and non-Euclidean space, and Euclidean and non-Euclidean space are both included in universal space. Each space constant with curvature being 1 over k squared, a real number, represents a unique space in universal space. In the definition of space curvature, each space curvature of the positive real number 1 over k squared greater than 0 represents a hyperbolic space. The space curvature of the negative real number 1 over k squared less than 0 represents an elliptical space. 1 over k squared equals 0 represents an Euclidean space, and so Euclidean space is a special case. In this book, we only discuss the hyperbolic geometry part. For elliptic geometry, we can use the negative real number 1 over k squared less than 0, with k substituted by 1k prime, to convert all of the hyperbolic equations to elliptic. Similarly, if based on the theory of the space constant, or k prime, for elliptical space, then the space curvature of elliptical space is 1 over k prime squared. This space curvature is also a positive real number, and under the definition of space curvature, each space curvature 1 over k prime squared greater than 0 represents an elliptical space. 1 over k prime squared equals 0 represents an Euclidean space, and 1 over k prime squared less than 0 represents a curvature in hyperbolic space. For hyperbolic geometry, we can use the negative real number 1 over k prime squared less than 0, with k prime substituted by ik, to convert all of the elliptic equations to hyperbolic. To sum up, if the space curvature of hyperbolic geometry is 1 over k squared greater than 0, and the space curvature of elliptic geometry is 1 over k prime squared greater than 0, then k squared equals negative k prime squared, or k prime squared equals negative k squared. And the space of Euclidean geometry is 1 over k squared equals 1 over k prime squared equals 0. And so, the consistency of space is very clear. Therefore, all formulas of elliptic geometry can be derived from the formulas of hyperbolic geometry. There is no need to create new formulas for elliptic geometry from scratch. Number 1. The formula of law of sine in hyperbolic geometry. Hyperbolic sine a over k over sine capital A equals hyperbolic sine b over k over sine b equals hyperbolic sine c over k over sine c, can be converted to the formula of law of sine in elliptic geometry. Sine a over k prime over sine capital A equals sine b over k prime over sine capital B equals sine c over k prime over sine capital C. Proof: let k equals ik prime. We have hyperbolic sine a over ik prime over sine capital A equals hyperbolic sine b over ik prime over sine capital B equals hyperbolic sine c over ik prime over sine capital C. Therefore, hyperbolic sine ia over k prime over sine capital A equals hyperbolic sine ib over k prime over sine capital B equals hyperbolic sine ic over k prime over sine capital C. And since hyperbolic sine ix equals I times the sine of x, therefore sine a over k prime over sine capital A equals sine b over k prime over sine capital B equals sine c over k prime over sine capital C. As a result, the formula of law of sine in hyperbolic geometry is converted into the formula of law of sine in elliptic geometry. Number 2. The formula of law of sine in elliptic geometry. Sine a over k prime over sine capital A equals sine b over k prime over sine capital B equals sine c over k prime over sine capital C. Can be converted to hyperbolic sine a over k over sine capital A equals hyperbolic sine b over k over sine capital B equals hyperbolic sine c over k over sine capital C. Proof. Let k prime equals ik. We have sine a over ik over sine capital A equals sine b over ik over sine capital B equals sine c over ik over sine capital C. And since sine ix equals I hyperbolic sine x, therefore sine ia over k over sine capital A equals sine ib over k over sine capital B equals sine ic over k over sine capital C. And therefore hyperbolic sine a over k over sine capital A equals hyperbolic sine b over k over sine capital B equals hyperbolic sine c over k over sine capital C. As a result, the formula of law of sine in elliptic geometry is converted into the formula of law of sine in hyperbolic geometry. Number 3. The formula of law over sine in hyperbolic geometry is hyperbolic sine a over k over sine capital A equals hyperbolic sine b over k over sine capital B equals hyperbolic sine c over k over sine capital C. And the formula of law of sine in elliptic geometry is sine a over k prime over sine capital A equals sine b over k prime over sine capital B equals sine c over k prime over sine capital C. Using 1 over k squared equals 0 or 1 over k prime squared equals 0, we can transform the formulas for law of sine in hyperbolic geometry or elliptic geometry into the formula of law of sine in Euclidean geometry. A over sine capital A equals B over sine capital B equals C over sine capital C. For all of the remaining formulas, they can be completed by the reader. From the consistency of space, we know that any real number, such as 1 over k squared, represents a unique space. Like a real number cannot include another real number, a unique space cannot include any other unique space. Conclusion. Known as the consistency of geometry, any space is nothing but Euclidean space, hyperbolic space, or elliptical space. The universe is no exception. As long as we know that the universe belongs to one of the three spaces of geometry, all the problems of the universe can be solved. So non-Euclidean geometry is the key to unraveling the mysteries of the universe. New discovery. No expansion of the universe still has redshift. coming soon. Number 2. Is the universe really expanding? I hope not. Number 3. Einstein's new clothes. Number 4. Big Bang. Do you believe it? A. Have you ever seen a singularity with no volume and no mass? B. This singularity, which has no volume and no mass, can it explode with 1,000,000,000,000 times more force than the atomic bomb? C. Can this explosion create the trillions of stars in the universe? Do you believe it? I don't. I believe it's nonsense. Number 5. A very important video. Unraveling the mysteries of the universe. A new discovery. No expansion of the universe, yet the universe still has redshift. Number 6. Upcoming movie. Young Diamond. How the young diamond baby did not graduate from primary school, did not attend junior high school and high school. From 5th grade, jumping directly to junior year of college. Got his master's degree in biochem from UCLA at 13, doctorate in biochem at 17, and MD from the University of Illinois at 22. The theory of young diamond. Every newborn child is a diamond. This diamond is alive. If the diamond is not polished each day, it will lose its luster. If the diamond has not been polished until adulthood, this diamond will become stone. Polishing it every day will illuminate its brightness. Growing up is bound to be a success. If the child is not successful, it is not the child's fault, but because the parents did not know to polish the diamond. The purpose of Young Diamond is to help parents polish their diamonds, wake up parents to re-understand their children, and inspire new reforms in education. More to come. Young Diamond Movie Studio Production.